Hello, and welcome back to Aggressive Physics. Today's day 7, acceleration. One of the more difficult topics for students to grasp is acceleration because it's a little abstract. It actually involves the speeding up or slowing down of objects. Now, things accelerate when they move faster or they move slower. And specifically, the definition is the rate of change of velocity. And the way a lot of definitions work is they actually give us the formula within the definition. Anytime there's a rate of change or rate of anything, that typically means that we're dividing by time. So in this case, the equation is going to have something divided by time. The rate of change of velocity, well, that means that we're going to divide velocity by time. So the equation is simply A equals delta V, change in velocity, over t. But I think it's important to understand it conceptually before we dive into it mathematically. Now notice, I did say velocity. So, what type of variable is velocity? Was it a scalar or was it a vector? And hopefully you remember that it was a vector quantity, which means that it has direction associated to it. So when we deal with a velocity, we're going to have to worry about the direction the object is moving in. So an acceleration is going to be determined by how much an object speeds up or slows down in a specific direction. So since velocity was a vector, acceleration will also be a vector. Remember that we're dividing by time, and time was a scalar quantity. So if you start with a vector and you divide by a scalar, you continue to have a vector at the end. Now, for example, let's say a car accelerates at 5 meters per second squared. How fast will it be moving at every second? Now, the way acceleration works is it means that the speed of the object in the direction it's traveling, so the speed plus direction, which is velocity, will change by that amount every second. And you'll notice the value I gave for the acceleration was meters per second squared. We're actually dividing meters per second by seconds. Some books will denote that as meters per second per second. So you have two division signs within the unit. I find that to be a little confusing, so I'll put the 2 seconds together and I'll just combine them to make them seconds squared. Most textbooks and the Regents examination uses meters per second squared for acceleration in terms of its units. Now remember, meters and seconds are base units of the metric system. When we combine them together, we form a derived unit. So meters per second squared is actually a derived unit. Now I've stalled long enough. How fast is this car going to be traveling every second? Now all we have to do is add 5 meters per second to each second. So at the first second, we were traveling at rest to begin with. After 1 second, we'll be traveling at 5. After 2 seconds, 10, then 15, then 20, then 25 meters per second. So when we have a car accelerating at a constant rate of 5 meters per second squared, it will be traveling fairly quickly after 5 seconds. We're talking about 20 meters per second. Now, typically that'll be a little more than 2.2 times in miles per hour. So that'll be over 50 miles per hour or around 50 miles per hour in about 5 seconds. So that's akin to a sports car accelerating from 0 to 60 miles per hour, in about 5 or 6 seconds. Now, we're going to use the metric system, so we're going to have to get used to that in terms of science versus maybe our everyday understanding of, speeds of vehicles or things like that. So acceleration rates can be used to determine the performance of cars, typically sports cars, but even things like minivans or buses can have performance indicators based on their acceleration. Now, as humans, we know when we accelerate. We can detect it in our bodies. And one of the ways that we do that is by our fluid in our ears sloshing around. And I know sloshing is not a very technical term, but in terms of this discussion, as the fluid changes its levels, your body knows that it's accelerating. We actually pay amusement parks to accelerate us. If we were to go to an amusement park and sit in a chair and just sit there, we wouldn't really have much fun. So instead, we expect them to take us up into a roller coaster and drop us down a steep hill, spin us around in circles, accelerate us quickly, and then stop rapidly as well. All of these things cause our bodies to experience the sensation of movement. If we don't accelerate, we really don't know that we're moving. If you travel in an airplane at a constant rate, and maybe you're at a cruising altitude, and you're traveling at a couple of hundred, miles per hour, well, you don't even realize that you're moving. The visual cues aren't up in the atmosphere as readily as on the Earth. We don't have trees to look at. We don't have houses or signs to observe that we know mentally don't move. So if you're traveling in an airplane, above the cloud level, you won't be able to have any cues to determine whether or not you're moving. You may be able to look down, if there aren't clouds, and see that the ground is traveling, but you're so far away that it's as if you're not traveling that quickly. Experience some turbulence, and you'll know right away that you are accelerating. So the turbulence will cause your stomach to lurch, your innards to kind of move up and down, to be in free fall slightly. And those are the experiences that your body actually knows you're accelerating. So we as humans feel acceleration. We might not really necessarily feel constant motion. Now, if we think about it, anytime we change velocity, we're accelerating. So traveling in a circle, you will accelerate even if you travel at the same speed. So if you're turning on a car at 30 miles per hour, what you'll experience, and it's 30 miles per hour the whole time, you'll experience acceleration even though the number for miles per hour stays the same. Now, when we talk about circular motion a little later, we'll see that the calculation is slightly different than what we've talked about already. But effectively, acceleration is any time we start or stop or turn, and our bodies feel. I remember as a child falling asleep in the back of my parents' car coming home from my grandparents' house. The car ride was about an hour, and I often fell asleep while we were on the highway. Well, every time we got off the highway, and I would wake up. Every time that we got to the house and drove into the driveway, I woke up. Now, the reason those experiences happened wasn't because my parents slammed on the brakes. It wasn't because they were trying to awaken me. What happened was my body experienced the acceleration. When we exited the highway, you were traveling at a constant rate. Back then it was 55 miles per hour. And my dad or my mom would turn the car off the exit ramp. Well, as soon as we turned off the exit ramp, my body detected the motion and I woke up. Once again, when we got to the house, we'd pull into the driveway and stop the car. And it didn't take a rapid slamming of the brakes in order to do that. Instead, it was just a gradual slow down and my body detected it and I would wake up. My dad slammed on the brakes, I would have ended up falling off the seat. Now, speaking of slowing down, we often use the term deceleration in everyday language. Instead, what I want to do in this course is just use positives and negatives to denote the direction of the acceleration. Deceleration in our common language would mean that it's slowing down. But sometimes you can have a negative acceleration and actually speed up. So what I want to do is stay away from the term deceleration. I know that sometimes we'll use it when we're talking about certain problems, but typically I want to stay away from it because I want to avoid the confusion that deceleration is always a negative acceleration. For example, if I were to drop an object, it would accelerate towards the ground. The acceleration of gravity would pull it towards the surface of the earth. Now, the acceleration of gravity is down, and I would denote that as a negative value. But the object's going to speed up. So I want to avoid the negative connotation, if you will, of using deceleration as a term. Negative isn't a bad thing. It's just going to be a direction. So we're going to use positive and negatives to denote direction as often as possible because it's going to be a lot easier to use positive and negatives in a mathematical equation. It's hard to calculate east and west. We don't really know what to do with it. But we do know at this point how to deal with a positive value or a negative value. Now, how can we tell if an object's going to speed up or slow down? Well, if the acceleration and the motion are in the same direction, the object's going to speed up. If the acceleration and the direction of motion are in opposite directions, the object's going to slow down. So we can tell just by the direction of the object's movement and the direction of the acceleration whether or not we're speeding up or slowing down. Thinking of a car. If you hit your gas pedal, well, that's going to provide a positive acceleration in the direction you're moving. So if I'm moving east, the accelerator will make me move east in a more rapid manner. So in that case, both the acceleration and my motion are east, I speed up. Now, I'm traveling east and there's a stop sign. Well, I hit the brake. When I hit the brake, that's going to provide an acceleration in the westerly direction. So since it's going west, I'm traveling east, the acceleration is west, I slow down. So just knowing the direction an object's moving and the direction of the acceleration can help us determine whether or not an object is going to speed up or slow down. When we travel in circles, things get a little different than that, and we'll talk about that more later. But just knowing the direction of the acceleration and the direction of motion will help us determine what direction the acceleration or what type of motion we'll have, whether or not an object will speed up or slow down. Now, I talked about it before, but I wanted to get into it conceptually first. But quantitatively, acceleration has a pretty simple equation. The acceleration is the rate of change of velocity. So the equation is going to be a, and the a is going to have the half arrow symbol because it's a vector. It's going to equal change in velocity, so we use the delta symbol, delta v, half arrow over the v because of the vector quantity, divided by time. Now, if we remember from math class what change in delta means, a lot of times we used it when we talked about slope, change in y over change in x, so delta y over delta x. It represented in math class typically x2 minus x1 or y2 minus y1. The second y versus minus the first y, or the second x minus the first x. Well, in physics, we often don't use ones and twos to denote beginning and end. Instead, we use initial and final. So the delta v represents vf, which is our final velocity, minus vi, which is our initial velocity. Now, for some reason, we take this equation, delta v over delta t, and rearrange it to fit within our reference table. So on the reference table, the equation is rearranged so it's vf equals vi plus at. I guess it costs more money to put equations over fractional form than in a single line. So what we're going to use is equation as vf equals vi plus at for most of our acceleration calculations. But if you want to just remember that it's the rate of change of velocity over time, that would make it easier to remember delta v over delta t. Typically the initial time is 0, so we often just use over t instead of delta, but typically it is the change in time for the problem. Now, that being said, most objects we're going to deal with in this course especially are going to have constant acceleration or uniform acceleration. Uniform means it's the same throughout the whole problem. Now, most vehicles in the real world, most objects in the real world do not have uniform acceleration. Cars, when they shift gears, will change the rate of acceleration. You know that because you feel the jerkiness during the accelerating during the gear change. If you're using a standard, you have control over that. If you have an automatic, you have control over that. You don't have control over that. Now, in my car, the shift from first to second gear is quite dramatic. I definitely know I'm changing from first to second gear every time because the car lurches forward as it's traveling. My transmission is not in top form, we'll say. Now, if an object has uniform acceleration, then what we can do is combine equations. And what's important to realize is that the average speed just becomes the average of the initial and final speeds, or in this case, the initial and final velocities. So I can use the initial velocity, which in many problems will be 0, or the final velocity, which in many problems will be some number, or it could be that you start at a certain speed and stop, so the final velocity may be 0. But if we have uniform acceleration, and for example, we go from 0 to 25 meters per second, well, the average velocity will be the average between 0 and 25. So mathematically, I do VI plus VF and divide by 2. In this case, it would be 12.5. If I started at 10 and I traveled to 30 meters per second, so 10 meters per second to 30 meters per second with a uniform acceleration, my average speed would be 20 meters per second. So mathematically, all we have to know is that the average of the initial and finals will get us the average velocity. It's nothing fancier than taking two numbers, adding them together, and dividing by 2. If you want to look at it as an equation, though, you'll do V bar equals VI plus VF over 2, which is just your equation for average. Now, it could be that an object doesn't have uniform acceleration. For this course, like I said, most objects will have uniform acceleration. The acceleration will be constant. One of the most common accelerations that we'll use will be the acceleration of gravity, be it on the Earth or the Moon, because that is typically a constant value near the surface of the Earth or near the surface of the Moon. Near the Earth, it's 9.8 meters per second squared. If you want to get a little formal, it's 9.81 meters per second squared. If you want to round it out and be more casual, we use 10. We just average, round the 9.8 to 10, and we use 10 meters per second squared. On the Moon, it's 1/6 that of the Earth, so if you take 9.8 and divide by 6, you'll get 1.63 meters per second squared. For some reason, we don't use a more casual or a more formal version of the acceleration of gravity on the Moon. Typically, 1.63 is it. Maybe in terms of formality, you have to wear a spacesuit to be on the Moon, so you need to be pretty formal to get there. So you're not allowed to wear jeans and a t-shirt or shorts and a t-shirt on the Moon. If you did, you'd die. So I think it might be important to realize that 1.63 is our standard value for the acceleration of gravity on the Moon, as formal as 9.81 would be on the Earth. Typically, our problems will have uniform acceleration. If we didn't have uniform acceleration, if it's a real-world problem, such as standard transmission or even automatic transmission, then we have a changing acceleration. And a changing acceleration is actually known as a jerk. So when you call someone a jerk, you're actually calling them a changing acceleration. Now, I think that's mostly because of their mood change or their attitude change. But in terms of strictly science, calling someone a jerk would mean that they are changing their acceleration. So I do have one thing to ask as we end today. What would x bar delta A mean? And I'll leave that to you to figure it out. This was day 7 of Agrosive Physics, and I thank you.